Question 13, 14 and 15. Which compound has the highest boiling point? So what you're looking for is you're looking for the strongest intermolecular bonds. The strongest intermolecular bonds are hydrogen bonds. It's where within one of these molecules you've got a hydrogen bonded to an oxygen, a nitrogen or a fluorine. And the bond between the hydrogen, the oxygen, the nitrogen, hydrogen, the oxygen, or the hydrogen, the nitrogen, or the hydrogen, the fluorine is very polar. So you get large delta plus and delta minuses set up, and then that attraction between those polar bonds and a neighbouring molecule is called a hydrogen bond. It's just basically a very, very strong dipole-dipole attraction. The next next highest boiling point is that where you've got polar bonds. So say for example a carbon bonded to an oxygen, or a carbon bonded to a Cl, or a carbon bonded to a Br, or a carbon bonded to a fluorine. So you've got a polar bond there. It's not as strong, it's not as polar as a H bonded to an O, or a H bonded to an N, or a H bonded to an F that's really polar and got large delta plus and delta minuses. But it is polar if you've got a C bonded to a Cl, an F, a Br, an I, or an O. And that would have the next highest boiling point, and the kind of intermolecular bonds between those kind of molecules are called dipole-dipole attractions. And then if you haven't got any polar bonds within the molecules, you've got van der Waals forces, the force of attraction between the electrons in one molecule and the nuclei, the positive nuclei in the neighbouring molecule, and that's the weakest form of intermolecular bond, and that would have the lowest boiling point. So first of all, I'm looking for highest boiling point. I'm immediately looking for a molecule with a hydrogen bonded to an oxygen, a hydrogen bonded to a nitrogen, or a hydrogen bonded to a fluorine, because that's going to be really polar. And then if that's really polar with large delta plus delta minuses, you get a really strong dipole-dipole attraction to the neighbouring molecule called a hydrogen bond. Butanal, let's go through these then. Butanal has got a carbon to oxygen double bond, so it's polar. You've got delta plus and delta minuses. On the neighbouring molecule you'll have a polar bond, and you have dipole-dipole attractions, but it's not a hydrogen bonded to an oxygen, or a hydrogen bonded to a nitrogen, or a hydrogen bonded to a fluorine. So the polar bond between the carbon and the oxygen is not as polar as it would be if you had an H to an F, an H to an O, or an H to an N. So medium boiling point. Yeah. Butan-2-ol, here we go, we've got an OH in there, you've got an oxygen bonded to a hydrogen, so that's going to be very, very polar, that bond, and so an O to an H is going to have a large delta plus on the H and a large delta minus on the O. Very, very polar bond, very, very strong intermolecular bonds, hydrogen bonding. B is going to have the highest boiling point probably. Of all of these, but let's go through them. But-2-ene is a hydrocarbon, no polar bonds, so intermolecular van der Waals forces between those. Now this is a tricky one because it's got fluorine in there, an F, but it hasn't got an F bonded to an H. It's got an F bonded to a carbon, so the F bonded to the carbon in one fluorobutane is going to be a polar bond, and therefore you'll have dipole-dipole between them. So dipole-dipole, dipole-dipole, medium boiling points, low boiling points for this one with no polar bonds and van der Waals. This one's got hydrogen bonds because it's got an oxygen bonded to a hydrogen. Your answer is B. Which statement is correct about the fractional distillation of crude oil? Tricky question this. Zeolite catalyst. No, that's used for catalytic cracking, the breaking of long chains into short chains using a catalyst. Each fraction contains a mixture of hydrocarbons. Well, that's true. You might think when you do fractional distillation of crude oil, each fraction, each set of liquids is pure. It's not. It's still going to have a mixture because you're never going to get complete evaporation at any one particular boiling point. You're heating it up and you've got different boiling points within the flask, so different temperatures within the flask, so things will boil at different temperatures even within the flask, because you never get one precise temperature. And again, in the fractionating column, it's hottest at the bottom and coolest at the top, so you've got temperature gradients in the flask and the fractionating column, so you haven't got one precise temperature, so you're going to get a mixture of hydrocarbons boiling, even though as best you might try, you're trying to get pure fractions coming off. They're never going to be pure. So B is your correct answer. Gaseous fractions are formed by breaking covalent bonds. No, you don't break covalent bonds. You're not breaking covalent bonds within molecules. When you're actually heating something up and making gases out of liquids, when you're evaporating these during distillation or fractional distillation, you're breaking intermolecular bonds, bonds between molecules, not the covalent bonds within the molecules. The fractionating column is hottest at the top. No, it's hottest at the bottom because you're heating the flask up at the bottom. That's where your heat's been provided from the bottom. So it's hottest at the bottom and then coolest towards the top. How many structural isomers with an unbranched chain have a molecular formula C4H6Br2? So I'm going to do spoilers here. So where can the BRs be? They can both be at carbon number 1, both be at carbon number 2, one at 1 and one at 2, one at 1 and one at 3, one at 2 and one at 3, and one at 1 and one at 4. And those are all your combinations, and that's why it's 6, answer C.